This video is intended to be an introduction to 3D printing. So we're going to look at a few different kinds of printers. We have a maker bot, we have a printer bot. We're going to talk about how they work. We're going to talk about the different terminology that you're likely to hear surrounding 3D printers so that you know what we're talking about when I use a term like hot end or build plate. We are going to do a few experiments, a few 3D printer experiments. We'll print some random objects. We'll print them both the right way and the wrong way so you can see what happens when your printer settings are not the way they should be. And we'll look at how you can avoid certain issues to get the most out of your prints, both in terms of time and in quality. So one of the first terms you're going to hear is 3D model. A 3D model is generally what we call the three-dimensional design that you've built on the computer. What a 3D printer lets us do is take that virtual 3D model that you've created on a computer and output it physically to something that you can actually hold in your hand. Let's start with the basics. Let's look at how to create something very simple in Fusion 360.
We're going to create a really simple shape here that we can do some experiments with. I'm going to create just a cube, a 2x2 by 2 inch cube, and I can actually use my mouse to drag out to 2x2 by 2 inch. But if you want to be more specific and make sure you get it just right, you can type in the numbers that you want in these fields here. And even though I was set up for millimeters, I can type in IN to make sure I get inches instead of millimeters. To export this, we're going to go up to the 3D print option. Make sure you have this checkbox here, send to print utility unchecked, so that you can save it as a file instead of instantly sending it to your slicer software. I'm naming my STL file now 2x2x2 cube and saving it to the proper folder.
So now that we've generated our 3D model, our 2x2 by 2 inch cube, we need to print it. But before we can do that, we have to use another piece of software called a slicer. A cube is one of the simplest forms that we can make with a 3D printer. There's just not much to it, right? So we know what a cube is supposed to look like. The 3D printer needs to build up layer by layer. So what the slicer is going to do is break our cube up into many, many layers, and it's going to build from the bottom up to the top. With a cube, this is really easy to understand. The more complicated the shape is, the harder it is maybe to wrap your head around, which is why we're starting with something simple like a cube. Okay, let's look at a physical example of this and how it works in practice, right? So here is a 2x2 inch square. This has been laser cut out of cardboard, and it's a good stand-in for our first layer. Our second layer, in this case, is also a square. In fact, every layer is going to be a square. So what your 3D printer is going to do is draw a square, and then another square, and then another square. And even though they're thin, over time, they build up and up and up until you have a cube. So you can see here we have multiple layers that are fused together. I mean, in this case, they're just stacked on top of each other, but you can imagine them fused together to create a 2 inch cube. The software that we're going to be using to generate our slicer files, our 3D print files, is either going to be Cura, which is pretty much an open source software that works with many different printers. The other piece of software we'll use is called the MakerBot software. So the printer behind me, the Holy Cross printer, is a MakerBot, and so we'll use MakerBot software to create files for that printer. My personal printers are printer bots, and we'll use the Cura software to do the slicing for the printer bots. I think it's good for you guys to see a couple of different types of software and how they're used. You're going to find that they are pretty much the same thing. It's mostly just the interface that changes. So what our printer needs to do is to create these stacked layers. So they're two-dimensional layers, but they do have a little bit of thickness. So by building them up and up and up, we end up with a three-dimensional object. The most common kind of printer, and the ones that we're going to use, are called extrusion-based printers. Extrusion is a term that may be unfamiliar to some of you. Some of you may know exactly what I'm talking about. But I guarantee you have all used an extruder at some point in the past. When you squeeze toothpaste out of a tube, you're basically extruding toothpaste. Another common example would be Play-Doh. A glue gun is a very good stand-in for how an extrusion-based 3D printer works. You've got this large piece of plastic that goes in through the back. The glue gun heats up that plastic, and then there's a nozzle with a small hole that squeezes out a bead of the hot glue. So you're extruding or forcing this larger piece of plastic through the back where it gets heated up, and then you're extruding a much thinner bead of that same plastic out the front, right? So that's in principle what extrusion is. And a 3D printer works almost the same way. You have a spool of plastic that feeds in through the top of what's called the hot end. This part right here is called the hot end, which is essentially just a small heating element that warms and heats the plastic to its melting point. And then there's a motor that pushes this thicker strand of plastic into the hot end and forces it out the bottom where it's extruded through a tip. So every 3D printer, extrusion-based 3D printer, will have a build plate. They come in different shapes and sizes. This is a 6x6 by 6 inch 3D printer, so it can print 6 inches from one side to the other and 6 inches from front to back, and it can print 6 inches high. So at its largest, we could print a 6x6 by 6 inch cube using a printer like this. Our MakerBot printer is similar, but it can print 10 by 6 by 6. So it can print 10 inches wide, 6 inches deep, and 6 inches tall. The way a 3D printer like this works, an extrusion-based printer, is by laminating layers together. Laminating means sticking multiple layers together. So if we were to take these squares that we printed out of cardboard and glue them together, we'd be laminating the sheets together to form a solid. Right now, they're just loose. Again, if we were to glue them together, we'd be laminating them into a solid. The 3D printer is going to work in a similar way, but it doesn't need glue because the plastic sticks to itself. So every layer that it builds, the molten plastic sticks to the previous layer, and it builds up that way. Our first layer doesn't have plastic to stick to, it has to stick to the build plate. This is a point of contention for many 3D printers because the plastic needs to stick well enough that it doesn't lift up or fall off while it's printing, but it can't stick so well that you can't remove it when it's done being printed. So there's a balancing act when you're setting what's called your Z height, and that's the height your extruder nozzle is from your build plate. Generally, you want that height to be about the thickness of a sheet of printer paper, just white, plain printer paper. That's a pretty good thickness so that the extruded plastic has just enough room to squeeze out from underneath the extruder and stick well to the build plate. If you're any closer, a couple of things can happen. One, if the print nozzle is directly against the build plate, there may not be enough of a gap and the plastic won't come out, and then you can get a jam inside your extruder nozzle because the plastic is like backing up inside the hot end. If you're too far away, there's too much of a gap between the hot end nozzle and the extrusion nozzle, the tip, and the build plate, and then your filament, your extruded filament will just squeeze out and it won't even stick to the plate. It'll just, it tends to stick to the nozzle and move around with the print head, and that doesn't work either. The good thing for us is that generally when we're 3D printing an object, we care more about what the outside looks like than what the inside looks like. So in this case, with these cardboard stacks, it's completely solid all the way through. Every layer is a square. But if we only care about what the outside looks like, theoretically, we could print this so that it's hollow inside. By making it hollow inside, we save time because it doesn't need to print an entire square-shaped layer as it moves up from the bottom to the top. We're also saving materials because we don't have to use as much plastic to print each layer. We're gonna run into a few problems if we make it completely hollow. First of all, our cube might be pretty weak because the walls will be relatively thin and the inside will have no structural support to it. The other issue that we have is that by the time it gets to the top and it needs to print a full square on the very top, there's nothing on the inside to support it. So you end up with a really droopy top layer. So what we need to do is create something called infill. Infill is a lattice-like grid that is created inside your 3D object. Once again, your slicer software is going to do most of the math for you. You don't have to design your infill in Fusion 360. You can create a solid object, and then once you bring it into your slicer software like MakerBot or Cura, you can tell your software what you want your fill percentage to be. Now, a common fill percentage for something like our cube would be 15%. That means 85% of the interior space in the cube will be open air, and 15% of the interior space will be a grid. The grid gets built on top of itself so that there's a structure inside. So the lattice not only gives it strength, it makes it more rigid. Think about how a suspension bridge works. But it also gives it a lattice like scaffolding for that top layer to print across so it doesn't droop down into the model file.
This is our MakerBot slicer software. We can directly import that STL file that we created, and you can see that it places it directly on our virtual build plate. And the virtual build plate is great because it lets us see how large our object is and where it's going to fit, and if it'll fit, and what orientation it's going to be. These settings I'm pretty much going to leave alone for now, but I'm highlighting the infill, which I'm going to leave purposely at 100% right now. That means every layer is going to be printed completely. There won't be any hollow space inside this print. By doing a quick preview, we can see how long the print will take, and it should tell us roughly how much material it's going to use. All we're really interested in knowing is how long it's going to take right now, and it says 6 hours and some odd minutes. But it'll probably take a little bit longer than that. There's extra time needed for the hot end to heat up and some extra processing time. So I'm just going to name this file. So this is different from my STL file. This is my slicer file that I'm going to load on an SD card and pop into our 3D printer. The 3D printer can't just print a raw STL file. You need to give it what's called G-code. And this slicer software is generating that for us right now. Here's a time lapse of our cube being printed. Now this is the 100% infill version, so there's no lattice on the inside of this print. It's completely solid all the way through. Every layer is a square, and it ended up taking roughly 7 hours to print. By comparison, this is exactly the same cube, but our settings are a little bit different in our MakerBot software. We set this one to have 15% infill, so there's a nice lattice-like grid on the inside that's holding everything together. We're going to weigh this later and take a look at what we're actually saving, but in terms of time, this print only took about an hour.
Okay, let's do some comparisons now. Here is the first cube we printed. It's 2 by 2 by 2 inches. It was printed with 100% infill.
So every layer is solid. There's no negative space inside. It's completely solid, and it feels completely solid. It's very heavy. In fact, it weighs 157 grams. Now we'll compare that to this cube, which is identical in terms of scale. It's the exact same model. So all the work we did in Fusion 360 is exactly the same. It's the same model. But when we brought it into the MakerBot slicer software, we made some changes, right? It's still 2 by 2 by 2 inches, but instead of 100% infill, we only have 15% infill. And let's see what difference that makes. 38 grams. So it's used way less material by having that infill than by not having infill, right? So the solid block is really strong. It probably has very good compression strength because it's solid. This one, maybe it's a little bit weaker in terms of compression strength, but it's still a solid block. It's not gonna deform on me. I can't bend it, I can't twist it. The lattice work inside is extremely strong. The other difference that we noticed that you may not have seen in the time lapse, because the time lapse is a little bit deceiving, this blue cube took 7 hours to print, whereas this white cube only took 1 hour.
I thought it would be fun to show you what the inside of the 15% filled cube looks like. And you might get a slight sense of this from watching the time-lapse video, but if I cut the cube in half, we can really take a look at what that infill lattice structure looks like and how it's built. Not all printers will print exactly the same way. This MakerBot uses a honeycomb pattern inside, so you can see there's a lot of strength in there. You can see the way the lattice holds itself together. Other printers might use a square or diamond pattern or even triangle shape pattern, but in the end, it's all about giving strength to the object on the inside without adding a lot of weight. The shape that we're going to build now is only slightly more complex than our cube. We're going to create this T shape that has an inch base. It's 3 inches tall, so it's 1 by 1 inch at the base, 3 inches tall, and then it'll have these two 1 by 1 by 1 inch arms that'll come off the top. And this is just complex enough that we can learn a little bit about how a 3D printer deals with things like overhangs. And we'll see, we're just going to print this right away using the same settings we used for the cube, and we're going to see what happens, and hopefully it will fail spectacularly.
Because this printer was trying to lay down a layer in mid-air, there was nothing for it to adhere to, so you end up with this spaghetti string, and it's only when it starts to connect to the edges of the T here and build out and out and out that it's able to retain that kind of shape, so you end up with this sort of like odd angled wedge under here instead of a nice flat bottom, and you have all of this stringy material that you're gonna have to like cut off or sand away. So not only is the shape wrong, but you have all this extra work to do to clean up the print. So this is not gonna work.
This time we're gonna add supports to our model. With the MakerBot software, it's as easy as clicking on the print settings menu and checking the box for breakaway supports. Let's see what happens when we print it like this.
In our second example, we had support materials turned on,
right? Support structures. So this nice grid of scaffolding that rides up along with the actual printed layer. So this is designed to just break away. And you'll see that our scaffolding actually failed because it didn't adhere well to the build plate. On this side, we had this nice support material, and again, this is designed to just break away, so I can sort of pull on it. Sometimes I'll squeeze it and sort of compress the layers to snap it, and then wiggle it until it pops free. There we go. So that's broken free, and now you can see the shape is what we're looking for. There is a little bit of that support material kind of clinging on to the bottom. So there's some finishing work that we're gonna have to do when we use support material, right? It's just a little bit of extra plastic that's grabbed on. There's a bit of a tooth to it, but a little bit of sandpaper. Sometimes I'll use like an emery board or a small piece of sandpaper to take some of that down. We have a print that has come out well. So here's our T with support material. Our T with support material. It worked all the way up. It still didn't adhere very well. And in the next video, we're gonna talk about why, and we're gonna troubleshoot that. But in the meantime, we can break away some of this. There's our T, printed well. So one of the things we can imagine with this type of printing and the need for support material is to try to solve these problems, these printer problems, without using support material. Let's imagine this is our build plate, right? Our T printed like this on the build plate, and gravity has pulled the filament down. So we have this stringy mess down here. But with the support material, there's something for the print to land on, to build across. But support material kind of sucks. It makes things ugly. Even when it works well, you still get messy bits that you have to then sand off. It's so much better if you don't need support material. The easiest way to print this without needing support material is just to print it like this. And now it doesn't need any kind of support material at all because it builds this larger layer first, and then it builds the thinner layer up to the top. Think about your prints. Now your prints are going to be much more complicated than this in all likelihood, but that doesn't mean these principles don't apply. We tend to want to look at our objects right side up when we're creating them, when we're designing them, and when we're printing them. But that last step, that printing step, looking at them right side up or in orientation isn't always the best way. So yes, in orientation, this is how we want our T to look, but the reality of things, when we print it, it probably makes more sense to print it upside down. So you always want to look at your objects from different angles to see which way it would be best to print to require the least amount of support material for any given object with any given printer. When I was learning how to 3D print, a lot of the mistakes that I just made intentionally, I did not make intentionally. I was making errors because I didn't know what I was doing. That's kind of how a lot of people started off 3D printing when it was a newer type of making. There weren't a million tutorial videos out there, and the software was a little bit harder to use, so it was easier to make silly mistakes that would lead to prints failing on the print bed, spaghetti messes all over your 3D printer because the extrusion failed, or it came unstuck from the build plate and just started extruding the spaghetti mess of plastic everywhere. So hopefully the videos that I'm showing you will prevent you from running into these same mistakes or having to make these mistakes on your own. I hope this was informative. Thank you for watching.